So good afternoon. We're going to start Unit 2 today. In Unit 2, we're going to work with functions. Remember last time we were working with lines, we were talking about the equation like y equals mx plus b. And notice how it's what we call a two-variable equation. Two-variable equations have what's called input and output. So usually the x is referred to our input value. Remember, it has to go through a series of calculations, and the result is what we call our output value or our y value. So we're going to kind of build on the topic of lines in Unit 2. So some vocabulary we're going to come across. We're going to see this word relation. We're going to see this word domain, range, and we're going to see this word function again. We're also going to be able to identify if a relation is a function. We're going to identify if a two-variable equation is a function. We're going to talk about function notation. We're going to evaluate functions. We're going to determine the domain of a function. And we're going to work with operations involving functions. So this is kind of a busy lesson, so hang on. So we can come up with here. So first off, domain, range, and relation. So let's first off look at this word relation. A relation will be described here as a set of ordered pairs. So notice how we have this word set. That's when we use these braces. So a relation will be described as a set of ordered pairs. And we talked about ordered pairs last time in graphing lines. The word domain, what it will represent is it's going to be the set of x values. And the range will be the set of y values. Sometimes mapping is used to understand what a relation looks like. So as I said, mapping is sometimes used to see the relationships of the domain and range. So if I want to map the following relation, notice I have a set of ordered pairs. We have this -2, 5, this -1, 3, the 3, 7, and the 4, 21. Those are our 4 different ordered pairs. If I want to map, what we do is we put the domain in one spot. So we have this -2, we have this -1, we have this 3, and we have this 4. And over here we have our y values, a 5, a 3, a 7, and a 12. Mapping just kind of says the -2 is going to correspond with the 5. In other words, the -2 is going to be assigned the y value. The -1 is going to be related to the 3, or the -1 is assigned to the 3. The 3 is related to the 7, or again, the 3 is assigned to the 7. And then the 4 is related to the 12, or again, 4 is assigned to the 12. So we kind of map it like that. So you see drawings like that, they call those mappings. So they're showing the relationship of how the domain and the range are tied together in that format. Kind of like a T-chart in some ways, just a little bit different. So if I want to identify the domain is going to be the set of x values. So again, I use the set notation, and I have a -2, a -1, a 3, and a 4. If I want to identify the range, it's going to be the set S. We use those braces again. We have a 5, a 3, a 7, and a 12. That would be our set of our ranges. So they're just essentially the y values listed. So that's what a relation is. A relation right now is going to just be basically a set of ordered pairs. And then the domain is going to be the x values, and the range is going to be the y values. And they're going to lead us to our next topic, which is what we call a function. So a function is going to be a special relation. In this situation, what's going to happen is each x value is going to be assigned exactly one y value. In other words, what this means is the x value cannot repeat. So if I look at the above function, at the above relation, is it a function? Well, if you look up there, notice that if we look at our ordered pairs, I don't see an ordered pair that has the same X value. And notice how we have this kind of a one-to-one correspondence. The -2 was assigned to 5. The -1 is assigned to 3. I don't see the input value being assigned except just one Y value. So in this situation, since I don't see the X's repeating and there's just kind of this one-to-one representation, is the above relation a function? We would say, yes, it is. So looking at the following relation. Again, we can make a mapping, and that can help us kind of understand the relationships between the ordered pairs, between the domain and the range. So notice how we have these 4, 1, 2, actually there's 5 ordered pairs. So notice how we have the -4, the -3, the -2, the -1. And notice how we have that -4 again. So I don't have to write it down twice. And over here I have the range is going to be a 4, a 3, a 2, a 1, and a 0. So now those repeated. So I have this -4. Notice how it's kind of mapped to or assigned a 4. The -3 is assigned the 3. The -2 is assigned a 2. The -1 is assigned the 1, but the -4 is also assigned a 0. So notice how this is just a relation, but notice how if I look at this in my domain, we see that there's a set of -4, -3, -2, and -1. And in the range, we see the set of this 4, this 3, this 2, this 1, and the 0. They don't have to be put in order, but if you want to put them in numerical order, that's fine. I just kind of lay them out there. But notice how is this relation a function? And notice how in this situation, notice how the -4 repeated up here. What that means is the -4 actually was assigned 2 different Y values. And remember by the definition, as we said up here, the X values can only be assigned one Y value. So this fails with respect to being a function. So we do have a relation here, but since the domain was assigned 2 different Y values, it's not called a function. So is this a function? We would say no, it's not. So that's kind of the beginning introduction of functions as we just talk about ordered pairs, domain and range. As we move further, we're going to start talking about a function as an equation. So if we talk about a function as an equation, as we recalled with lines, the X values are going through a series of calculations, and it's going to be assigned exactly one Y value. So again, note here, Y depends on X. So Y will not go through any calculations. The X is going to be going through the calculations. So if I want to determine the following equations to see if there is a function or not, right, yes or no. Notice how if I look at the first one, I kind of like just draw this little input output kind of concept. Notice the X is going to go in and the Y's are going to come out. So remember the domain goes in, it goes to a series of calculations, whatever they are, blah, 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 just something going on inside there. So if you look at this first one, what's going to happen is, you're going to have 5 and, some number X is going to be squared minus 2 times some number plus 3. Notice if you pick a number for X and if it runs these calculations, so for instance, if I pick the number 2, I'm going to have like 5 times 4 minus 4 plus 3. I'm going to have 20 minus 4 plus 3. 16 plus 3 would be 19. So notice that the 2 went in and it outputted a 19. So that's kind of modeling what we're seeing here with respect to a function. X is going in, it's going through some calculations, and it's only being assigned one Y value, the 19 in this case. I don't see a situation where this would not happen. So equations that look like this, they're going to look like, they're going to represent a function. That's going to be a yes. If I look at like y equals 7 over x, notice we have a domain restriction, x cannot equal 0. But if I leave that out, if I look at the rule, 7 divided by some number, I can pick any number I want. Say if I pick, say, 7 divided by some number, let's say, we can say 2. 7 divided by 2, in other words, 2 would go into 7, maybe it'll be like 3.5 or something. Notice how when you put the 2 in, it does kick out just one answer. So I don't see a situation where you would get 2 different answers. You're just going to be dividing 7 by a number, and there's no way you're going to get 2 different answers. So an equation that looks like this would also be considered a function. Notice this equation here looks a little wonky to begin with because it's not y equals. One of the catches, the y should not be going through any calculations. And notice how here the y is being squared. Squaring does unusual things. So for instance, if I pick, say, x to be, say if I pick x to be a 3, I have this 3 squared plus y squared is equal to this 25. Notice how 3 squared is a 9. And you have plus this y squared is equal to 25. And notice how if I subtract 9 to each side, I'm going to get this y squared equals 16. At this point, one of the things we look at is if you square a number to get 16, y could either be a positive or a negative 4 here. So when 3 went in, notice how it actually could be assigned a 4 or a negative 4. So that y squared kind of causes an issue here. So as I said, one thing is the y shouldn't be going through any calculations. And secondly, if I do pick a value for x, I'm seeing that it's going to assign 2 different y values for it. So equations that look like this is going to be a big oh no. It's not going to be a function. Similarly, if you look at this equation here, y equals plus or minus 2x, notice how it already kind of looks a little weird. Got this plus or minus here. That's kind of almost like what we had over here. Notice how, again, if I pick a value for x, say if I pick an easy number like 2, 2 times 2, well, that's going to be plus or minus the square root of 4. Well, the square root of 4 is going to be a 2. That means I'm going to get plus or minus 2. So notice what this is saying is 2 went in, but it's being assigned 2 different y values. It's being assigned 2's being assigned to a 2, and the 2's being assigned to a negative 2. So notice how you cannot have that. You cannot have an x value being assigned 2 different y values. So notice how, again, as ordered pairs, you're seeing that x repeat. So equations that look like this will also be considered not a function. So they're an equation, but they don't fit the category of a function. And we're going to be focusing more on functions in this chapter. So function notation, there's always this little special notation. So we're going to use this notation like f of x. It's going to be used in place of y. So if I want to write this in function notation, I replace the y with this f of x. So it's going to represent the output value. The x is going to still represent an input value. So now we have this notation of a function. So f of x is how I say that. And f of x, like I said, is going to equal that 2x plus 1 there. So I kind of noted that right there, actually. So when you see that, a y can actually be replaced with, I don't really need all this. The y can be replaced with just that f of x. So as we move forward, you're going to start to see the y value disappear, and in its place, we're going to start to see this f of x appear in its place. So as we move forward, we're going to have to start evaluating a function. Again, what's inside the parentheses will will be substituted in for x, and then the expression will be simplified. So if I give you the function f of x equals 2x squared plus 3x minus 5, the way we evaluate this, notice how there's a 0 in place of x. Notice how there's a 0 inside the parentheses. That 0 is going to replace, it's going to become our input value. So the 0 is going to go in place of x, and we have to perform the operations. So again, if you want to put this in the calculator, you can. 2 times 0 squared plus 3 times 0 minus 5. Or again, we know that 0 squared is 0 and 2 times 0 is 0. 3 times 0 is 0. 0 plus 0, and then you have that negative 5 there. So we see that negative 5 would be the answer. So when you have f of 0, notice how 0 is the input value, but f of 0 represents the output value or the y value. So notice how, again, this represents what y is. So that's the same thing as y equals negative 5. So when x is 0, y is equal to negative 5. But instead of using this notation, you're going to start to see this more commonly used. So if I want to evaluate f of 1, to evaluate f of 1, what we do is we put a 1 in for x. Notice how the 1 is replacing x. So we replace x in our function. So 2 times 1 squared plus 3 times 1 minus 5. I'm going to have to work across the page since I didn't make enough room. So following the order of operations, 1 squared is 1. 2 times 1 is 2. So you have 2 plus then 3 times 1 minus 5. So now I have to multiply 3 times 1 is 3. So I have 2 plus 3 minus 5. Well, 2 plus 3 is 5, and 5 minus 5 would be 0. So that means that f of 1 would actually equal 0. In other words, the output value or the y value is equal to 0. Or again, now we're using the word domain and range. So notice how our domain value was a 1 and our range value was a 0. So if I want to evaluate f of negative 3, again, the negative 3 is going to go in place of x. So if you want to pause here and see if you can work that out, and feel free to use a calculator. You don't have to do this all by hand. So if I'm following the order of operations, negative 3 squared is 9. 2 times 9 is 18. 3 times negative 3 is a negative 9. And we also have that negative 5. So that's going to be 18 and a negative 14. 18 and a negative 14 would be then a 4. So again, f of negative 3 is going to equal then 4. And that's what we mean by evaluating a function, is we're looking for what's called the output value or the range value. So again, f of negative 3 represents y equals 4. So if I want to evaluate f of negative x, notice now we're not going to actually get a number. We're going to replace x with a negative x now. So this is now going to be then 2 times negative x squared plus 3 times negative x. And then we have this minus 5. So here we're just, simplifying is all we really can do. We really can't actually get a number here because we didn't replace x with a number. We replaced it with a negative x. So remember, a negative times negative is a positive. So that first part's just going to be 2x squared. And 3 times negative x is going to be a negative 3x, or we can call that a minus 3x, and then minus 5. So basically what we have is another expression, or again, we would call that a quadratic expression there. So f of negative x is the same thing as 2x squared minus 3x minus 5. So that's what we get there. Now notice how this time we have a negative on the outside. So this means to take the opposite of f of x. So remember, we have the opposite of, and then f of x is just simply this 3x, I'm sorry. So we said 2x squared plus 3 times x minus 5. And so the negative here just means to take the opposite of the function itself. So all we do here is just change all the signs. So that ends up being negative 2x squared, a negative 3x, and then a positive 5. So negative f of x basically just means to change all the signs. So that means you have negative 2x squared minus this 3x plus 5 as your answer. Notice I have 3f of x. So notice how the 3 is on the outside. So this means to multiply the function by 3. So what this looks like is you have 3 times then 2x squared plus 3x minus 5. So now we just multiply the 3 through the parentheses to remove parentheses. That's the distributive property. So we end up with then this 6x squared plus this 9x minus this 15. And again, those are not like terms, so that stays as the answer. So 3f of x is going to equal then the 6x squared plus 9x minus 15. And this one here, notice how I have to replace x with x plus 3. So again, this one's unusual. So we have 2, and then the x gets replaced with x plus 3. So wherever there's an x, I'm going to replace it with this x plus 3. So I have this x plus 3 squared, plus then I have this 3 times this x plus 3. And then I have this minus 5. So x plus 3 squared, I may have to do this off to the side. X plus 3 times x plus 3. So I have to multiply the x through. That's going to be x squared. And then you're going to have 3x. Then you got to multiply this 3 through. So again, you're going to get a 3x again. And 3 times 3 would be 9. So that's going to be this x squared plus this 6x plus 9. Also remember, if I have x plus 3 squared, there's a special shortcut that says just square the x, multiply the 3 times the x, and then multiply by 2. So 3 times x is 3x times 2 would be 6x. And then you just square the 3, and 3 times 3 would be 9. So if you want, you can recognize this is a shortcut that if you square a binomial, it's going to turn into a trinomial. To get the first term, you just square the first term, x squared. To get the middle term, you multiply the 3 and the x together, and then double it, or multiply by 2, gives you 6x. And then you square the last term, and that gives you your trinomial. So what I have now then is this 2 times this x squared plus this 6x plus this 9, plus then this 3 times this x plus 3 minus this 5. So then I need to multiply the 2 through the parentheses to get rid of parentheses. So it's going to be 2x squared plus then 12x plus 18. And then I got to multiply the 3 through the parentheses. Since it's a positive 3, no sign changing. So it's going to be a 3x plus a 9. And then you have this negative 5 on the end. So then we just combine like terms. The quadratic term, I'm only seeing that 2x squared, so it just comes down. The linear term, what I'm seeing is there is this 12x, and there's this 3x. So as far as those go, that's going to give me a 15x. And then your constant. Notice how we have an 18, a 9, and a negative 5. So actually I have to add 3 things. 18 and a 9 would be, say, 27. And then lose 5 would be a positive 22. So plus 22. So f of x plus 3 turns into this expression. So that one requires a little bit of that math we did back in the earlier units, in unit 1. So that's one of the things you may have to do in your homework is start to play with evaluating functions by replacing x with whatever they give you. The next thing we have to do is determine the domain of a function. The domain starts out as all real numbers, but there are certain things that you can't do. So there are certain functions that the domain will need to be determined. So some things we look for if there's an issue with the domain. If the domain has the x in the denominator, set the denominator equal to 0 and solve for x. This will have to be excluded from the domain. So I should have said domain here. I probably said if the function has x in the denominator. Okay. The other one is if the variable is inside the square root symbol, that should be not set the denominator. That should be set the inside to greater than or equal to 0. So that's a mistake on my part. So set the inside. So if the variable is in the inside of the square root, then set the whole inside to greater than or equal to 0. And we'll talk about that more. So if I look at this first function, do you see a denominator? In other words, I don't see a bottom number. There's not a fractioner, so there is no domain restriction. Also, I don't see a square root symbol. So since it has neither one of those, there's not going to be a domain restriction. So our domain is going to be the set of all real numbers. So a lot of times we use a capital R here for that. And sometimes, they may also use interval notation. So they may say from negative infinity to infinity, that would represent all real numbers as well. So something like that would be what our domain would look like. If I look at this next example, I have x squared plus 9 in the denominator. In other words, x is in the denominator. So if we set x squared plus 9 equal to 0, if I can find a value for x that makes that true, we have to exclude that from the domain. So if I try to use factoring, if I use 4 square, the quadratic term goes here, the constant goes here. So what are the factors of the constant that give you the middle term? Remember, since the middle term is not there, its coefficient must have been 0. So what are the factors of 9 that give you 0? Well, only thing I have is a 1 and a 9 and a 3 and a 3. And the only way to get 0 is one of these has got to be negative. So if I have a -3 and a 3, that would give me 0. But notice that a -3 and a positive 3, if you multiply those together, does not give me a positive 9. So I can't use that either. So I can't make that negative because I need them both to be negative to get a positive out of that. So we can't just make one of them negative. We have to make them both negative, and a negative plus negative is not going to give me that. A -3 plus -3 is not going to give me 0 either. So what we pick up on is this is not factorable. Now, another thing we could do to solve this is I can get the x squared by itself. But to do that, I have to move the -9 over here like this. And one of the strategies is to take the square root of both sides. This becomes the plus or minus the square root of -9. And what this becomes then is plus or minus 3i. So what this tells me is what makes the denominator 0 is an imaginary number. And right now, our domain is involving real numbers, so we're not involving that this time. So since I didn't get a real number solution on the bottom, our domain again is going to be the set of real numbers, or the set of R, or we can use the interval notation from negative infinity to positive infinity to represent the set of real numbers. So again, there is no domain restriction on that one. If I look at x squared minus 36 on the bottom, that one looks familiar to me. X squared minus 36 is equal to 0. Notice how there's a subtraction sign this time. That's a different squares. We pick up on that being x minus 6 times this x plus 6 is equal to 0. And so we get, x would equal 6 and -6. So again, those would be what we call domain restrictions. So if I do it the other way, notice I have x squared minus 36 is equal to 0. You can also just move the 36 over. X squared equals 36. you can take the square root of each side, but when you do that, you have to put a plus or minus the square root of 36. And notice how it gives me, again, a positive or negative 6. So again, those are going to be restrictions. So your domain could also be written as like the set of x's such that x cannot equal 6 or negative 6, something to that nature. So we have those restrictions there. So sometimes they'll use like set builder notation in your homework. Notice on this one right here, we're having a square root symbol. Again, as we talked about, you cannot take the square root of a negative number, because remember, if we take the square root of a negative number, that gives us an imaginary number. So there is a domain restriction here. So 7x minus 21 has to be set to be greater than or equal to 0. What that means is we're looking for non-negative numbers. And so we solve inequalities like we solve equations. So we can add the 21 to both sides, 7x equal, or sorry, greater than or equal to 21, divide by 7, so x is going to be greater than or equal to 3. One thing to bring to your attention, though, is when solving an inequality, as I said, the steps are the same as linear equations. But there's this but here. If the coefficient is negative, when you divide both sides by negative, that inequality symbol must flip to keep the statement true. But notice how our coefficient was positive, so we didn't have to change the inequality symbol. But if that was a negative 7 and we divided both sides by negative 7, that inequality symbol would have had a flipped. So luckily we didn't have to deal with that. So if I'm using set builder notation, our domain is going to be the set of x's such that x is greater than or equal to 3. Oops, that looks like a brace. So greater than or equal to 3. And then I put my little brace. So that would be a way that you could be writing your domain is in set builder notation. If I was using interval notation, notice how you would say bracket 3 going to infinity, like that. Notice how you have to use a bracket because we're including the 3 here. Usually if it's set builder notation, we use an inequality inside there, typically. It just depends, but that's the most common way of doing it. So lastly, operations involving functions. We have basically 4 basic operations: adding, subtracting, multiplying, dividing. That's what I mean by operations. Adding, subtracting, multiplying, dividing. So one of the things we're going to pick up on is you're going to see this notation, f plus g. What that means is we're going to have more than one function here. One function is going to be called f, and one function is going to be called g. F plus g means basically just add the 2 functions together. If you have f minus g of x, what that basically means is subtract the 2 functions. So f goes first, g goes second in the subtraction. If you have f dot g, notice how this just really means multiply. So this means f times g of x. So basically what we do here is we just multiply the 2 functions together. And if we have f over g, that's just going to be the same thing as f of x over g of x. So this notation is really a shortcut for this over here. So we're going to be given functions f and g, and we want to find the following parts. It also says, parts a through d also determine the domain. So these first 4, once we get our new function, they want us to find the domain of our new function. So f plus g of x just means to go 2x plus 4. That's your first one. And what you're adding to that is 3x minus 4. That's the second function. And since we're adding, really these parentheses weren't necessary, so it's just drop the parentheses, 2x plus 4 plus 3x and a negative 4. And combining like terms, the 2x goes with the 3x, gives us a 5x. And the 4 and the negative 4 would zero out. So our new function Again, f plus g of x is just going to be 5x. Now, when it says domain, again, if you don't see a fraction where there's a variable in the denominator, there's not a domain restriction. If we don't see a square root symbol where the variable is inside, there's not a domain restriction. So since we just have 5 times x, the domain is going to be the set of all real numbers. So if you want to use interval notation, you can see it as the set of x such that x is an element of R. You may see it written like that, which is fancy for all real numbers. So this is kind of like a little e for element of. So like I said, if I was using interval notation, I would just say negative infinity to positive infinity. There aren't any domain restrictions. So now if I do f minus g of x, so now how f is going to be this 2x plus 4. And we're going to be subtracting the second function, which is this 3x minus 4. Now, since we're subtracting, remember we have to do the subtraction part first. So that becomes then this negative 3x plus 4. Remember, we have to change the signs to remove parentheses. So now I have this 2x plus 4 comes down, and then we just combine like terms. So a 2x and a negative 3x. Remember, we just had the coefficients. So 2 plus negative 3 would be a negative 1, or we just call that negative x. And 4 plus 4 would be 8. So I'd have negative x plus 8. So f minus g of x would equal then this negative x plus 8. So notice again, there's not any domain restrictions because there's not any fractions with the variable in the denominator. There's not a square root symbol with a variable inside the radical symbol. So we have no domain issues here. So the domain is just going to be all real numbers. So the domain is going to be, again, the set of x's such that x is an element of R. Or again, we could write it as negative infinity to infinity if we're using interval notation. So in Blackboard, I'm not really sure which way they do that because it seems like they mix that up a little bit. So we just have to base it on each question. So now I have f times g of x. So that means I have to go multiply the two together. So 2x plus 4 times 3x minus 4. So this is where, again, we use FOIL or distributive property or 4 square, whichever way you do it. So I'm just going to multiply the 2's got to go through each piece, and then the 4's got to go through each piece. So we have to do actually 4 multiplications to work this problem out. So 2x times 3x is going to give me this 6x squared. 2x times negative 4 is going to be negative 8x. And then 4 times 3x is going to be a positive 12x. And 4 times negative 4 is going to be negative 16. So then we clean it up by combining the like terms in the middle. So 6x squared, that's going to be negative 8x plus 12x, which is going to be a positive 4x minus 16. So that's our multiplication. So f times g of x is simply going to be this new function. And notice again, there aren't any domain restrictions here because there's no fractions or radicals. So again, the domain is going to be the set of x's such that x is an element of R. Or again, we could also say interval notation negative infinity to infinity. So my last one here is I have f over g, so that's division. So it's going to be 2x plus 4 over 3x minus 4. Notice the numerator can't be factored any because there's not a GCF and it's just a linear. So linear doesn't factor. It's got to be quadratic or something to factor. And so the only way to cancel out 2x plus 4 is to have a 2x minus 4 on, or 2x plus 4 on the bottom. Since I don't see a 2x plus 4 on the bottom, we can't touch it. It stays as 2x plus 4 over 3x minus 4. So that's our new function. But also there is a domain restriction because 3x minus 4 is in the bottom. So what we did is we set 3x minus 4 equal to 0 and solve for x. So 3x would equal 4. Therefore, x would equal 4/3. So that basically means we can't equal 4/3. So as far as the domain goes, the domain is going to be the set of x's such that x cannot equal 4/3. That's kind of how we write that in set builder notation. Interval notation, what we basically do is you go like negative infinity to 4/3, but you can't include 4/3, so we use a parenthesis in union with. So we also put that in union with. So the other side of it would be from 4/3 to positive infinity. If I was using interval notation, it would look something like that. So notice how that basically means we go everywhere except 4/3 on a number line. So the 4/3 is excluded. So union kind of means to put these two sets together as one big set. Now f plus g of 3 basically means I go up here to the function. Notice how f plus g of x was, notice how it was this f plus g of x was this 5x. So to do f plus g of 3, what I'm doing is just going 5 times 3, since that's what f plus g of x was 5 times x. So 5 times 3 becomes then 15. So f plus g of 3 is just simply 15. Now I have this f minus g of 4. So if I go up there to my function, we said f minus g of x was negative x plus 3. So I have this negative x plus 3 here. So if I put 4 in, that means to take the opposite of 4 and then add 3. What's going to be a negative 4 plus 3? So that answer is going to end up being then a negative 1. So f minus g of 4, my output value or my range value is going to be that negative 1. F times g of 2, well, f times g of 2 is at 6x squared plus 4x minus 16. So 6x squared plus 4x minus 16. We try that again. 16. Okay. And so to evaluate this at 2, I replace x with a 2. 6 times 2 squared plus 4 times 2 minus 16. Again, feel free to use a calculator. I didn't bring one with me today. So 2 times 2 squared means 2 times 2, which is 4. 6 times 4 is 24. 4 times 2 is 8, and then you have to lose 16. So it's going to be 32 lose 16. That's going to just be 16. So 16 would be our answer there to that one. Now f over g of 1 just means to use the function that we came up with up there, which was, what was that function? That 2x plus 4 and that 3x minus over 3x minus 4. So I had this 2x plus 4 over 3x minus 4. And so what I have to do there is replace x with 1. So it's going to be 2 times 1 plus 4 over 3 times 1 minus 4. So 2 times 1 is 2. 2 plus 4 is 6. 3 times 1 is 3. 3 lose 4 would be a negative 1. So 6 over negative 1 would be the same thing as a negative 6. So that would be then a negative 6 as an answer. So it kind of takes us through unit 1, or I'm sorry, unit 2, lesson 1, starting to work with functions. So as we said, in working with functions here, you need to be familiar with the word relation, domain, range, what a function is. And remember, a function, each x value is assigned one y value, which basically means the x's do not repeat. We talked about function notation, things like that. So I'll stop there and we can kind of go from there.